Okay, last week we have started to talk about the device, which is the first one. The most important is the PN diode, PN junction. So we're starting from the PN junction. So basically, if you look at the structure of the MOSFET, inside the MOSFET, let's already have certain parasitic PN junction between the drain to the substrate and also the source to the substrate, and these two PN junction will highly influence the non-ideal effect for the MOSFET, so which is very crucial for the future. So that's why that we always start from the discussion of the PN junction. Okay, so we have been already go through this one. So last week we have also talked about the first, if you look at the basic structure of the PN junction, which is a combination of the N region with the P region. So if we try to combine these both together, so something definitely will happen in this interface. That's where we call as a junction. So in this case, we consider a little bit higher for P-type doping, that we call as a P+, and a little bit lower on for the N-type doping, where we have N here. If we only consider for the diffusion mechanism, and for sure that the first one we will see the hole, because we have a higher hole concentration here, and therefore the hole will start to diffuse to the right hand side, and we have the higher electron concentration in this region, so we will have electron diffusion to the left hand side. So that's the first very basic phenomenon that we should be able to have in mind, that if we put the two different concentration semiconductor together, that for sure that the first one will be happen for sure. It's a diffusion mechanism. But if we only have a diffusion mechanism, that for sure that this in the end, the semiconductor material will all have the same P and N doping in the whole region, which is not true in the reality. So for sure this means that we will have some other mechanism that will try to balance this diffusion mechanism. So again, if you try to look at the PN junctions here, so we have the P in the left hand side, we have an N in the right hand side. So the first of all, as the electron diffuse from the N region, so we will have the electron will diffuse from N region to the P region, and because of some part of electron will being diffused to here, which means that the positive charge donor atoms are left behind, where we start to see the positive charge will be left behind because of the negative charge, the negative electron diffused to the left, and therefore positive charge donor atom are left behind. So we will first to see, we will have this positive charge here. And similarly, the holes diffuse from the P region, and to the hole will diffuse from P to N. So similarly, we will foresee the negative charge will also left in this region, because certain part of the positive holes are diffusing to the right. So we will have a negative charge here. And therefore we will see a spatial region that both contain the charge here. We have a positive charge, we have a negative charge, and normally we call this charge we call the space charge. So these charge that have a certain charge moving, and then you left a certain another opposite charge. That is sometimes we call as this space charge, and therefore this region will contain the space charge, and this is we call the space charge region. And also sometimes we not only call a space region, sometimes we also call as a depletion region. So the negative, positive, and negative charge in the N and P region that can also induce an electrical field. Because right now we have the positive charge here, we have a negative charge here, so therefore we will have the internal electric field induced from in this direction. This is our electric field. So because of this negative positive charge and negative charge that will induce the electric field in this space charge region, and therefore this electric field will try to stop the diffusion, because originally we have the diffusion of holes from left to the right. We have a diffusion electron from the right to the left, and because of this electrical field here, so therefore we will start to see the balance between the hole diffusion so we have the hole diffusion from left to right, and then this is going to be balanced by the electrical field. So this electric field will try to stop the hole diffusion. And similarly, we have the electron diffusion. We have an electron diffusion from the right to the left, and therefore this also internal induced electric field, because of this space charge, will try to balance this electron diffusion. So under the equilibrium case, the diffusion and the diffusion force and the electric field will exactly balance with each other. So this is the reason why that we won't see this semiconductor will become as a material that has an equal electron and hole concentration in the P and N region, because of due to this space charge and create this electrical field, and this electrical field will try to balance the hole diffusion and also will balance the electron diffusion. So that's the reason that once we try to put the P and N together, and then immediately we will see this internal electrical field inside this P and N space charge region. So since right now there's no voltage applied across this right now we don't apply any voltage, so there's no voltage applied across this PN junction, and therefore the junction is in thermal equilibrium. And we also consider, because this is under the equilibrium case, so the Fermi energy level must be constant throughout the whole entire system. Because this is under equilibrium, so the Fermi energy level should be constant across the system. So now if we try to look at the band diagram for this PN junction, so right now we all knew that once we connect the PN, and there's a space region will happen. So we will have a space charge region here. So with all what we knew from previous knowledge about the band diagram, we will be very interested to use the band diagram to analyze this PN junction. So let's do the one by one. First of all, we look at what would be the band diagram in the P region. So as usual, we have the conduction band, valence band here. EC, EV, and because of this is a P region, which means our Fermi energy is close to the valence band. Right? So that's the previous very fundamental related to the N and P. So the Fermi energy must be close to the P. Must close to the valence band. But because this is under the equilibrium case, so the Fermi energy should be constant through the whole system, which we have the Fermi energy should be constant through the whole system here. So now if we look at the right hand side, which is the N region. So N region, as we know that in the N-type semiconductor, the Fermi energy must be close to the conduction band. So in the N region, we can expect here our Fermi energy will close to our conduction band, and therefore we will see our band diagram something like this one. So now, of course, in the one system, the conduction band should also be continuous, and the valence band should be continuous. So we can expect these regions probably like this one. And also the valence band will be probably like this one in the region of the space charge region. So electron in the conduction band of an N region will see a potential barrier if you consider you are as electrons in this region, and this is a region that is an N type, so we have the lots of electrons here. So this electron, if you look at the the electron's viewpoint, the electron will see a kind of a barrier here, because of the electron want to flow to the left, which means that the electron have to overcome these barriers. So this is something that we call as a built-in potential barrier. This is something we call the built-in potential barrier. And because of this built-in potential barrier, this electron is not be able to flow to the left, because this electron see a kind of a barrier will try to stop the electron diffusion. So electron in the conduction band of N region see a potential barrier in trying to move to the conduction band of the P region. This potential barrier is referred to as a built-in potential barrier. And which normally we call this as a VBI. And similarly, if you look at the viewpoint from the holes in the P region, which we will see a lot of holes here. The holes also would like to diffuse to the right because of high concentration, diffuse to the low concentration region. But also the holes will see this potential barrier. So therefore, this potential barrier will stop the hole diffusions here. So this potential VBI maintains equilibrium, so therefore no current is producing by this voltage. This is a voltage that we don't apply any additional bias, and then therefore the PN junction will internally form this built-in potential that will stop the carrier diffusion. And also, as we previously already mentioned, that in the band diagram we are interested in the conduction band, valence band, Fermi energy, but also there's one that we are interested in is the intrinsic Fermi energy, which is EFI. So the intrinsic Fermi energy will be just almost in the middle between EC and EV, and will be just in the middle between EC and EV. So we have the EFI here, we have the EFI here. And also we can try to calculate the EFI versus EF, which is what we generally consider also. Also the EFI is continuous in the system, which means that the EFI will be also connected like this one. And the difference between the EFI and EF, that's we call the phi FP. And also we have this one, that's we call the phi FN here. So therefore, the built-in voltage here is equal to this plus this one. Right, so that's the built-in potential between the the P and N can be estimated from the Fermi, the difference between the Fermi energy with respect to the Fermi level in the P region and also in the N region. Therefore, based on this very simple calculation, that we are able to start to estimate what is exactly the equation for the building potential. So, as we already mentioned, the VBI, the building voltage, which is equal to phi Fn plus phi Fp here. And also, we already knew that our equilibrium, thermal equilibrium electron concentration is shown here, and which also can be estimated from here. And where we have this equation that we already mentioned, so we just try to put this one, replace this one as a phi Fn here. And in here, we consider our thermal equilibrium, the electron concentration is completely equal to our donor concentration, which we consider as 100% of ionization. So the N0 is equal to ND. So therefore, we can first to have this equation. And similarly, we do the same thing for the whole concentration, and therefore we can have this phi Fp here. So now the goal is trying to find a way to estimate phi Fn and phi Fp here. So now therefore we just put these two equations together, so we got the VBI is equal to KT over, in here it's use a E, but it's a sense, sometimes use a Q, but it's a KT over E, natural log NA times ND over NI squared. And also, in most of the time, we just consider this term as a thermal voltage, which is a VT. So this is a VT natural log NA ND NI squared here. So this is a very famous equation. The building voltage is equal to VT times natural log NA ND over NI squared, and then the physics behind is pretty simple. And then to derive these equations are also very simple. But these equations are very useful because we are able to estimate the building voltage between the P and N junction. So now, since we have the potential, we have a voltage, so the next stage definitely we are interested in the electric field inside this space charge region. So because we already knew that an electric field is created in the depletion region, so therefore we are interested in how to estimate this electric field. So still we consider that we have these p-n junctions here. We have a P, we have a N, and then we have a space charge region here and here, which has a negative charge. We have the positive charge. And also we put as a distance here that we call as the width of this depletion width, this space charge region along the n side that we call as xn, and we put this width along the p side we call the minus xp here. So to start to estimate the electric field, we use a very basic equation that we call as a Poisson equation. So in the Poisson equation, we all knew that the second order of derivative of the potential versus x direction is equal to the charge equal to the minus the charge distribution along the x space versus over the dielectric constant. So that's this is a well-known the Poisson equation, and also this is equal to the first order derivative, the electric field dx. So based on this equation, as long as we can have the charge distribution, we are able to estimate the electric field. So now the first day is that if we can have the rho x, which is the charge distributions inside this x space, we are able to integrate, and therefore we can have the electric field distribution inside the space charge region. Once we have this electric field distribution inside the space charge region, we do the integration again. Then we can have this potential distribution in the space charge region. So the idea is still very simple. So now first what we have to understand is what is the charge distributions inside this space charge region. So similarly, we can first try to draw the charge distribution along the x direction, because now we have the positive charge in the xn and negative charge in the xp. So the charge distribution here ideally will be the charge that has this is x, this is along the x direction, this is our rho x in the y directions here. So first of all, we must have the positive charge in the positive x direction, and because of this, inside the space charge region we have the charge balance. So the amount of positive charge also will have the same amount of a negative charge here, and this is minus xp, and then the amount of charge will be equal to, will correlated to the concentrations. So this is a charge distributions inside this space charge region. So now with this charge distribution, we can start to have the rho x equation. Rho x equations in the region of a minus xp, between the minus xp and 0, which is minus ENA. And also the rho x in the region which is 0, between the 0 and xn, which is END here. So based on the goal is trying to integrate this term to get the electric field, and now we all have this charge distribution as a constant in this region and constant in this region, and therefore we can start to do the integration as shown here and with here. And the electric field also continues, which is continuous at the x equal to 0, and therefore we will have this result. So by consider this all the information here, we can have the electric field is equal to minus END x on s xn minus x, and also minus ENA x on s x plus xp. And based on this equation, we can start to draw the electric field distribution Ex versus x direction, which is equal to, this is minus xp, this is xn. So we have this electric field distribution inside this space charge region. And because of, as I say, at this point the electric field must be equal, so and therefore we can, by based on this equal to this one at the x equal to 0, we can get this formula. Okay, so the next stage we start to want to derive the potential, which is a similar goal like the previous one, but we integrate again from the electric field to the potential, and also based on this information, and we can start to integrate the electric field and the results shown in this one and also this one. So finally we have this potential distribution, the building potential between the minus xp to the positive xn, where we have the, like this one, first is a 0, and then the potential start to build up, and start to be the constant here, and this point is exactly the same where we have been mentioned. This is all potential inside this space charge region, which is our building potential. That's what we call as a VBI here. So the ideas behind is not that difficult. We just always starting from the band diagram, and we look at the fundamental equation, Poisson equation. This is not the new equation. This is the equation that you have been already learned from the undergraduate physics, from the basic physics. So as long as we have this charge, we are start to able to integrate as an electric field. And then once we have the electric field, we start able to integrate electric field as a potential. So with considering this equation at the x equal to xn, which is the VBI, here is S equal to xn is the building potential here. Then we have this equation. This is also the simple idea that if you start to work on the semiconductor, you know the semiconductor in this domain we have it divided by the fabrication, testing, and also there's a very important one for the simulation. So in the case of simulation, actually the fundamental equation we look at for the simulation is always first to look at the charge, which is this one. So the concept is the same. If you look at the TK simulation software, I would not say 100%, but I would say more than 80%. The device level based simulation, they always starting from look at how will be the charge, the distribution, and then start to do the computational to integrate as a electric field and then integrate as a potential. So this is the ideas behind for the simulation software, and this is just we also show me here. This is how we also derive from the charge to the electric field to the potential. So since now we have the potential, the next question is definitely we are interested in is that how large for this space charge width, right? Because we know that this could be the one critical parameter in their influence the charge, influence the electric field, and then how this space charge width determined. So that's the questions here. So as I say, sometimes we call the space charge width, sometimes we call as a depletion width. So the question is now become that how are we able to estimate this space charge in the P region and space charge width in the N region, and for sure the total width is equal to Sn plus Xp here. And we're starting from this equation where we already shown that the NAXP should be equal to NDXN here. By consider this equation, we can have this one, and also we have been shown this equation in the previous slide, where it has already the depletion width here. So now we just use this equation and try to make sure that we have the able to estimate the Xn and Xp here. So now this is the equation for Xn and this is equation for Xp. So by consider this one and put in the, for example, if you want to solve the xn, you just try to replace xp as a xn by using this function. So then we can try to solve this xn, and we should get this result, and also solve this one to get this xp here. So therefore, the total space charge width is Sn plus xp, which is equal to so that's a depletion width equation. Now you can see from this equation, the depletion width is also determined by the building potential, also determined by the doping concentration here. Because of also from this this W is a total depletion width. But if you look at the depletion width for the XP, so we actually also got the same, that our XP is highly influenced by our P-type doping. So this depletion width will be highly influenced by the doping in this region. So as you can see here, if we have the higher P-type doping here and higher P-type doping here, so basically we will have the smaller depletion width XP. So which means if you consider a particular junction, because in the junction we always not have the equal concentration between P and N, it's always in the case with a highly doped P or highly doped N. So therefore, if you consider the P plus N junction, which means that the P plus means that we have a higher P doping, and therefore we basically have the very narrow P depletion width XP here. So this actually gives us a good way to do some approximation, because in reality we always have this asymmetric doping concentration between the N and P, and now we realize that if we have a symmetry of N and P, probably we can try to do some interesting approximation. So for example, the ideal case, the most ideal case, but in reality it's not going to happen, is we have a P and N, and that has an equal concentration between the P and N. But this is not going to happen in reality. But if you look at the depletion width here, so we basically have the equal XP equal to Xn. But this is not going to happen. In reality, we will see most of the cases that we have this asymmetric concentration between the P and N. For example, with some particular extreme case where we discuss P plus plus over N here. In this case, because we have a very high P-type concentration, so ideally we will have the very narrow P depletion width compared to the N. So in this case, the XP will be much smaller than Xn. And also, another case where we have the P over N plus plus. And similarly, we will have the very narrow in the N depletion width compared to the P depletion width, which has a XP much larger than XN. So, in this case, what does these cases could imply for our device? Because this is just a PN junction, so most of us, when we learn this, probably will be just stop here, because now you realize that there's a concentration related to the depletion width change on the PN junction. But as I always say, that the most important is try to understand what this will be influenced on our real transistor, especially in the MOSFET. So therefore, if you look at the MOSFET structure, where in the MOSFET structure, most of the time, we have a P substrate here, for sure. And we also have the source and drain region here. So we have the P substrate here. And also we have the source and drain. But as I already mentioned, that we normally want to reduce resistance, no matter for contact resistance or source drain resistance. So we always make it as a N++. And in this case, also we have the gate here. And also the metal here. But based on the knowledge we know from the PN junction, this N++ P junction actually will create certain issues. Because this one is exactly the case, just like this one. Right? So what does this tell us? This tells us that inside this N++ P between the drain and substrate, actually we will have the depletion width very narrow here, but a little bit wider in the substrate. So this is our depletion width between the drain to the substrate in reality. So in this case, we will have the Xn much smaller than Xp, because normally we make a very high doping in the drain and source, but also the substrate we will make a little bit lower doping, because we don't want to have a very high threshold voltage. We will talk about later, but normally we will substrate will make us a little bit lower doping. So in the end, we will have very narrow in the drain, but also very wide in the substrate for depletion width. But now you will see this can be created certain issues, because now we have a certain space charge in this region. And as I already mentioned, that when the device is turned on, we apply the bias here. We start to have the electron diffusion. First we have electrons accumulation and inversion and accumulation. So in anyhow, we have an electron here. But the electron here will become the problem because this electron will start to influence by the depletion width here, right? So then you can expect that this wider of this region certainly will influence our transistor operation because of we have an electron here. But once at the moment, this electron will start to be influenced by this very wide space charge region. And that creates a certain issue. And right now we will explain detail later. When we talk about MOSFET, we will definitely need to use this depletion region again to understand the device operation. This is just an idea that why this equation is sometimes more important than just estimate depletion width in the PN junction, because in reality, PN junction is not going to be a device. But inside the real device, there are lots of parasitic PN junction. So this is one idea that this part can certainly influence our channel and influence our transistor operations. Okay, so in the previous case, we only talked about the zero bias. This is under the equilibrium case, but for sure that in reality, this device is never be used only under without any bias. We definitely will try to give the forward and reverse bias and try to look at their IV characteristic. So the first case we will discuss here is under the reverse bias. So reverse bias means that this is a simple PN junction schematic, and normally in the P side we call as an anode, and in the N side we call the cathode. And the reverse bias means that we put a high bias in the cathode side. That's what we call the reverse bias here. So therefore, right now we are interested in that what would be the characteristic, especially the potential, the building potential barrier change as we start to apply the reverse bias here. So in previous sections, we already knew that our building potential should be equal to our phi Fn plus phi Fp here. But now if we have this reverse bias, that can change quite a lot for the total bias, the total potential inside this space charge region. So, but still we're starting from the band diagram here. So first we look at the band diagram in the P region, where we have the still the same. We have the conduction band, we have a valence band, and because of this is P type, so therefore we have a Fermi energy close to the valence band. And again, now we have the N type, but the only difference here is that we have to be aware that this is not under the equilibrium, which means that the Fermi energy in the P and N is not the same, because this is not the equilibrium. So we have to use a quasi-Fermi energy, where we use EFP here. And now because we apply the additional bias in the cathode region, so therefore we will start to see the gap between the EFP and EFN, which is here. EFN and EFP, and the difference between the EFP and EFP here. This is exactly our additional reverse bias. So that's the main difference between the zero bias, because zero bias is the Fermi energy is continuous and then also constant in the system, because now we try to give additional bias in the cathode side, so that we start to have the imbalance of the carrier, because now we apply the additional bias, so we can expect that the liquid have a certain excess carrier, right? So where we already discussed, once you give the additional force, you will have the excess carrier. So therefore, we cannot use simple Fermi energy. We have to divide by the quasi-Fermi energy in the P side, that's we call the EFP, and quasi-Fermi energy in the N side, that's we call the EFN. And the difference between the EFP and EFN is just exactly the bias that we apply here, which is the VR here. So now, with all this, we can start also to build up the band diagram in the N region. Still the same, because right now this is the still on the right hand side, still the N type semiconductor. So our Fermi energy, our conduction band will still close to our EFN here, and we're far away from our EV. So this is EC, this is EV here. And the EC and EV still will be the continuous in the system. So therefore, finally, we have this band diagram like here. So now we will see the electrons in this N region will even see a more larger barrier cannot flow to the left, because right now our building barrier here, our building potential, these total barriers we need to consider, which is V total, which should be our original, that without any bias, VBI plus additional VR, because right now we give the additional VR here. And also for the intrinsic Fermi energy, still the same. This is our EFI, this is our EFI. So still we can use phi FP, and this one E phi FN, and therefore the VBI, as we already mentioned previously, the VBI is equal to E phi FP plus E phi FN plus VR. So, as shown here, V total is equal to VBI plus VR. Right now we consider there's additional VR here. And because of this additional VR, actually the barrier is become larger. The barrier is become larger because right now we actually create this VBR, so then the barrier height is become larger, so therefore our electrons even more difficult to flow to the left. Similarly, the holes become even more difficult flow to the right. And then the rest equation, the right is the same where we have. So now we have this depletion width total, but the only difference here is we add this VR. And then also the E max, the maximum electric field, is also related to this additional VR here. So once we increase our reverse bias, actually our diffusion width will getting wider and wider, which will further getting electron and holes will be very difficult to cross this large barrier height. So based on this understanding, actually if you try to think about the current versus the voltage characteristic, because in the end the goal is try to understand the current versus the voltage. In the diode, in the PN junction, we are interested in the current from the anode and also the bias in the anode region. And because right now we apply the reverse bias, so which means we increase the voltage towards this direction, because this VR is equal to V minus VA. And based on, we don't derive the current equation at this moment, but based on what we already knew, that we increase the reverse bias, our barriers increasing, our depletion width increasing. So ideally, we should get the current is equal to 0 as long as we apply the reverse bias, because the barrier is different. It's become larger, right? So the electron is getting more difficult. Your holes is getting more difficult. So ideally, in this region, we should have the current. This current we normally call as a reverse current. This current IR should be approached to 0, right? So based on this, based on the understanding of the barrier height and depletion width, so that's actually already enough for us to guess what would be the current characteristic as long as we increase the reverse bias. Okay, so now we understand under the reverse bias. So next one we will start to talk about additional concept which is very important, but in the basic semiconductor textbook normally just 1 or 2 pages talk about this, but for the practical testing, for the semiconductor practical testing, is very often have to use a concept like the capacitance. And here just show a little bit more to introduce a concept related to the junction capacitance here. Because right now we have the PN junctions, like because of due to the put the P and N, so we can expect we have this PN junction. So then first one, we just recap a bit about the charge distribution inside this PN junction, which we have this one. We have the charge distributions in the N region. We have the constant positive charge. In the P region, we have a constant negative charge, positive and minus at the Xn and minus Xp here. And right now, if we consider additional bias applied to this PN junction. But what can be we can have this additional bias. We can apply for DC. So we can first to apply for this DC reverse bias. So because of this DC reverse bias, according to the knowledge we have from last slide, once we apply reverse bias, we will see the depletion width become wider. So that will form this depletion width. This is mainly due to the DC bias. But in here, we try to make this a little bit more complicated because we want to see the charge's influence. And therefore, on top of DC, we apply the small signal AC, which means we have this AC signal here. So this is our AC signal. So therefore, the total applied bias should consider with a DC plus AC. And in certain region, we have this DVR, which is mainly come from the AC. So therefore, now the voltage here is VR. Sometimes it's increased because of this positive AC. Sometimes it's negative. So therefore, the bias here is become the dynamic. It's not a constant anymore. It's a VR, positive and minus the VR. And because of this positive minus, that additional bias will apply to our junction. That also will create the influence on our charge distributions, which this additional bias, additional AC, will also cause the additional change and the additional charge change, which is shown me here. And in this we have a minus dq prime and positive dq prime. And this is because due to this additional dVr. And that's also in the end will change our depletion width because due to the apply VR plus the VR. And this additional AC will influence the charge, but also influence the depletion width. And we all knew, if you look at the a basic capacitor definition, the capacitance is mainly related to the charge versus the voltage, which is shown here. So once we have this additional charge due to the additional bias, actually we can start to have this capacitance. So therefore, we can use this concept to estimate the capacitance due to this AC signal. That's where we call as a junction capacitance, because this is a capacitance between the P and N junctions here. So a capacitance is associated with the PN junction due to a separation of the positive and negative charge in the depletion region. So a separation of the positive and negative charge in this depletion width. An increase in the reverse bias, the VR, will uncover additional positive charge. So this will uncover additional positive charge and also additional negative charge. And that will create the capacitance. Therefore, we can estimate capacitance is equal to dq over dVr. And then the rest of a calculation is the same. The dq here just related to the additional xn, additional xp, and finally we can start to estimate this one and become show me here. So that's how we actually can use this junction and then put the additional AC, and therefore we can measure the junction capacitance. And one more important concept related to the junction is that, as we already mentioned, that in reality we won't have the junction that has an equal electron hole concentration. Is always a symmetric balance. So as I already said, that once we have a symmetric balance with a certain case, we can probably do the very interesting approximation to reduce the complexities here. So for example, if we have the junction where we consider this is a P++ versus a N here, and then we have them in the middle, this is a junction here, and therefore we can call this as what we consider as a one-sided junction. In this case, this is P++ versus N, so therefore the NA must be much larger than ND, right? And from the previous knowledge we already have, once we have a larger NA over ND, so then the distribution width in the P side must be smaller than Xn. So we have this is XP, this is Xn here. So therefore, the total depletion width is equal to XP plus Xn. Now, can be approximated to Xn. And this concept is what we call the one-sided junction. So, a spatial p-n junction called one-sided junction, where the p-type doping is much larger than the n-type, and therefore the depletion width in the p is much smaller than the n here. So therefore, you can start to use what we have equation, but now we consider this approximation, and also the previous one we have this junction capacitance. So finally, this actually in the end lead to the very useful approach where we are able to, by considering this equation, we can estimate the doping concentration, which is here. So how do we do this? So we actually just need to plot it as a 1 over c squared versus VR. And then we should be able to have this straight line where the slope is equal to two over E exo S N D. So by consider, that's why that we spend the time to talk about junction capacitance, because this is useful for us to estimate doping concentration, because this equation shows that the slope is related to the ND, and also the intercept here is related to the building voltage, where we have ND and building voltage here. So in the end, this becomes a very useful measurement techniques, because if you have a piece of the material where because normally, of course, in here we in textbook we will explain the reality issue, but the reality issue is that if you got a piece of the semiconductor wafer, how do you determine the doping concentration precisely, correctly? Of course, you can trust your wafer supplier. Your wafer supplier means that the wafer who sell to you, you buy from this vendor. But sometimes their information might not be correct. So to double make sure that the doping concentration is correct, we also need to have the very special test key on our chip to measure the doping concentration, because the doping concentration is, if the doping concentration goes wrong, that will entirely create many issues for the whole semiconductor device. So normally we will create this spatial structure that we have the a substrate here, and the goal is we want to find out what is our doping concentration in the substrate. And what we need to do is you just need to form a small P++ region in the one specific location of the wafer. Then we just do the P++. But normally how we can make it, we just implant. We do the implantation, so we will find the place that have the P++, and therefore we are able to form the capacitance between the P++ and also the N here. So the next one is with this testing structure, we just measure junction capacitance, and we just plot one over C squared versus reverse bias. So finally, we are able to estimate the doping concentration here. So that's a goal. That's a goal that we why we spend the time to talk about junction capacitance. Most of when I was a student, I also get confused that what would be the purpose. We need to learn the junction capacitance, because this is a very sometimes important, but sometimes it's easily ignored, because in the entire semiconductor physics textbook, with this scope of this class, there's no other place explain the crucials related to the junction capacitance. And then only the time when I start to do the real testing, I start to realize that this is a concept that we already learned, but just because of in the scope of this class, this is fundamental for everyone. We normally didn't mention too many for the practical case, but this just let you understand that why the junction capacitance and one-sided junction is simple, but in the end, it's powerful. Okay, so we will take a break for 10 minutes and we'll come back at 11.
章节这边，
对，
为什么 steady state condition 的时候我们要留一个 G prime， 但是我们在生物和地面的时候，我们会把它就是等于零这样子。
说是我看
为什么这个 G prime 是被保留在这个这种独立变异型？
因为你可以面看一下不会有那个、不会有那种derivation的这个 generation， 所以这边是考虑可以面换你 G 考虑怎样。
可是 steady state 不是应该？
它 steady state 只是 time dependent， 是对时间是 steady state， 对。但是你 initial 不是，所以我们重点是我们想要知道这个 addition 对时间的，对。
那可以理解成就是说，在这个情况下，它这个 generation 是持续有在生成，它不会因为时间而消失。
不是，它应该是说你的 generation 是随着时间它产生量是变少，因为你是一个 addition 的 carry 进去，所以我们有兴趣想要知道是说它那个 generation 对时间的它的 factor 是什么。所以我觉得它不是持续生成，只是纯粹知道那一个瞬间 addition 那个 G 它会对时间会变化怎么样。对。它只是说它 steady condition 只是说对时间来说是 steady。对，但它不代表一开始是这样。对。
所以其实这 G prime 应该要就如果写清楚一点的话，应该要就是在这边显示一开始我们给它的一个，就是一开始它的一个刺激的那个
对。
好，了解，下次。
确认一下，确认找不出。你有确认交换数吗？
还没有。
我看一下。说的 Depletion width， 还是那个？那你说是哪个
Emax。
这边吗？哦，对，哦，那有两根连着。
Okay, so just a reminder that there's a mistake for this equation where the NAND is on top and then the NA plus ND is on the bottom. Okay, so now we will start to talk about some non-ideal effects here. So in the previous, we mentioned that if you look at the typical IV characteristic, where we have the current, anode current versus anode voltage. So ideally, based on the concept that we have for the potential building barrier, the large building barrier, as we increase the reverse bias, the wider depletion width, as long as we increase reverse bias. So we can have the conclusion that ideally we try to apply the reverse bias should always the current is equal to 0 because of the barrier is just going to increase as larger as possible, and then there's no carrier can flow from P to N and N to P. So that's the ideal case. But in reality, once you really try to measure switch to the as larger as possible you can, then you will start to see some non-ideal effect, which in reality you will see the current start to increase and start to have this huge current increase. And this is the voltage that will cause this a huge current is normally we call as a breakdown voltage. So this is the concept that actually is very often to see reality, because it's not possible that we can sweep as a larger and the current always close to 0. It must be some limitation, and therefore we need to understand why there's a limitation, especially the mechanism related to this breakdown. And that's why we have this slide to try to explain the first phenomenon that we call the junction breakdown here. So the reverse bias might not increase without limit, as at some particular voltage the reverse bias current will increase rapidly, and the applied voltage at this point is called the breakdown voltage. And there's several different mechanisms related to breakdown voltage. The first one is we call the Zener effect. So the Zener breakdown occurs in the highly doped PN junction through a tunneling mechanism here. So this is an example that we have if we have the junction has junction like here, and in the left hand side we have the P plus, in the right hand side we have the N plus, and based on the concept that depletion width is in proportional to our junction capacitance. So once we have a highly doping, we will have a very narrow depletion width here. So therefore that could have a chance that these carriers, electron hole, might be able to tunnel through this depletion width and reach to the other side. And this is mechanism where we learn from the quantum mechanics. We already learned about that. This is the same one that we call the tunneling mechanism. So in a highly doped junction, the conduction and the valence band on opposite sides of a junction are sufficiently close during the reverse bias, and that electron might tunnel directly from the valence band on the p side into conduction band. So electrons can tunnel from valence band to the conduction band, which shown in here. So in this case, we also start to see this Zener effect that will have a huge leakage current, high current. That's also considered one of the junction breakdown because of a highly doped that causes a very narrow depletion width, and then we can start to see this tunneling mechanism. And this is in a very particular case that where we have this highly doped P and N junction. But the other one, which is most often occurs in every semiconductor device, that we call as an average breakdown. So the average breakdowns process occurs when electron and holes moving across a space charge region acquire sufficient energy from electric field to create electrical hole pairs by colliding with atomic electrons with a depletion region. So the idea is that we have the diffusion electron here, and then because this is very large, we apply the high bias, so the electron is being acquired with high energy. So now we have a electron that has a high energy. These high energy electrons can break silicon bonding. And once the silicon bonding is broken, so we have that can actually, you break the one silicon bonding, that can simultaneously to generate the electron and hole pairs. So now you create one more holes, one more electrons, and this electron will further acquire enough energy and start to break another bonding. So therefore, we will generate additional one more electron and hole pair. So in the end, this is kind of like the loop process. We will generate a lot of electron hole pairs. So we will have many electron and hole pairs generated. That's we call the average process. So the average breakdown occurs when electron and hole pair moving across space charge region acquires sufficient energy from the electric field, and in the end to create a lot of electron hole pairs. The new created electron hole move in the opposite direction due to the electric field and thereby create a reverse current. The new generated electron hole pair may acquire sufficient energy again to lead into the average process. For most of p-n junction, the dominant breakdown mechanism will be the average effect. So this will be the main dominant mechanism for the, not only for the p-n junction, p-n diode. Actually, in the MOSFET, we also have this average breakdown because in the MOSFET that we also have the p-n junction in the drain side. So that also can cause a breakdown in the drain side as well. So here's some more detail about this average breakdown, and this is a way that how we are able to identify the criteria that trigger the average breakdown. So in the beginning, we consider as an initial current here. This is a current that start in the beginning of the space charge region. But then, due to this avalanche process, that we will start to generate lots of electron hole pairs. So in the end, the current at the end of the depletion width must be several times larger than the initial one. So therefore, we define as a parameter called Mn, where Mn is a multiplication factor to describe that the overall the phenomenon due to this avalanche phenomenon. And next, we consider the Inx is equal to In alpha n dnx plus this one IP alpha p dx. This formula just try to understand that the current induced by the electron and hole separately, and where the alpha n and alpha p are the electron and hole ionization rate here. So we consider this equation. Finally, we can have this one, and in here we assume that the ionization rate for electron hole are the same, which is equal to alpha. So in the end, we can have this one, this equation. And once we have the multiplication factor Mn approach to the infinite, which means that if this one is integration between 0 to w is equal to 1, then our multiplication factor will be approached to the infinite, which will be the case of average breakdown. So the average breakdown defined to the voltage where M approach to the infinity. So once the N approach to infinity, then we can consider as the average phenomenon. So there's some additional small concept. I would not say it's not important. I would not say it's not that important, but still, it's interesting to know that in the junction we have all different variety junction. We also have this what we call linear gradient junction, where in the concentration in the one place is not that as a constant. So in this case, we have this is our PN junction here, where we have the ND is a constant, but in the P region, our concentration is varied with respect to the S location, and then especially this varies a linear change, so that's we call as the linear gradient junction. And also follow the same calculation where we can also able to estimate the electric field as shown me here, and also the potential. Then in here that I won't go through again because this is just a similar concept, but just so you can put all the different variables for the concentration, and then you will get the difference for the potential in the electric field. So similarly, with this non-uniform dope junction, we are also able to estimate the junction capacitance. And final, there's also the concept we call the hyper-abrupt junction, which is the same, just the doping concentration has a different kind of the distribution as shown here. This is n is equal to bx m as shown here, and then with all these concentration, we are able to estimate the C prime, which is a capacitance here, and this is sometimes they call the variegated diodes. This is just information that you can aware of that. It's not needed that you can put too much attention. I know for some of the field we might need this variegated diode, but at least in my field so far I never used this one, but I heard about that. I saw time to time, but just this is pretty like the domain dependent. I would say this is interesting to know. As long as you need it, you are always able to come back to look up, but nothing is needed to further too in-depth discussion here. Okay, so that's a final for this chapter. For we look at for the p-n junction. So we consider for p-n junction, we first have the diffusion, and then in the end we have this building electric field, and this electric field will cause the equilibrium, the balance with the diffusion mechanism. And also we have very important concept for this building potential. And also in this p-n junction, in this chapter we only talk about reverse bias. In the next one we'll talk about forward bias, because the next one we'll talk about how the current is formed. In the reverse bias, that we have a very wide depletion, we have very large barrier, and then that causes a very limited current. And also we have the concept between the capacitance and then the breakdown mechanism, especially very important one is called the average. And this phenomenon that the electron hole pairs can be continuously generated, sometimes we also call this phenomenon as an impermeabilization. These are the terms that very often mentioned together. The average breakdown, impermeabilization, they almost indicate the similar things. Okay, so that's the end of this slide. So we will start to move for the next one. Now we will start to move to the device. So in the previous, we only mainly focused on the physics between the P and N, but now we will look at in the little bit whole aspect that we consider as a PN as a device that we call as a diode. So we expect that we will learn that what will be the current transport in the PN diode. So that's very important, because as a device in the end that we hope to conduct the current in the one side. So that's why we need to understand why it's a current phenomenon, and also the ideal diode equation and minority carrier distribution, which is very important because we already mentioned that in the end the overall physics always dominated by the minority carriers here. And also the quasi-Fermi energy, quasi-Fermi level, this is same concept, because now we have the P and N, so we have these additional carriers under the different bias, so therefore there's no more the typical Fermi energy. We need to use the quasi-Fermi energy, and also some of the non-ideal effects will be also lectured in this slide. So the first one is the p-n junction current here. So in the previous case that we already mentioned that in the zero bias, in the case with the zero bias, we already knew that we have the constant Fermi energy across the whole system. And then on the left hand side, we have the P side, P region. And on the right side, we have the N region. So the Venn diagram will be drawn as shown here. So this is under the zero bias. and then the barrier between the N and P is that we call the VBI. Building potential, building voltage here. And also in the last slide, we mentioned about the concept under the reverse bias. So in the reverse bias, right now we don't have the constant Fermi energy. We use the concept of the quasi-Fermi energy, where we have the EFP here. We have the EFN here. EFP and then the EFN here. And then the voltage difference, the difference between EFP and EFN is determined by our reverse bias. And under the reverse bias, we still have the conduction band. But now, because of a reverse bias, will increase the barriers here. So this is here. So therefore, VBI plus VR. Now we have this barrier high here. This is a case under reverse bias, which will apply the positive bias in the cathode side. And because of this positive bias, this reverse bias, that will cause a large barriers, and therefore we won't expect to see any electrons flow, and we don't expect to see any holes flow. So this is something that we have been mentioned. But now we are interested in on the opposite case, which is the forward bias. So in the case of forward bias, the idea is very similar to reverse bias, but completely in the opposite way, where we still have this Fermi, quasi-Fermi energy, but now we apply the positive bias in the, we have the positive, this is a positive here. And negative here, where we apply the VA forward bias here. So the forward bias actually will cause this EF goes up, and therefore now we have a EFN, something like this. EFP, EFN here. And this actually will cause a difference in the barrier, because right now we still have this. This is a P region. But now on the right hand side is the N region, and therefore conduction band is become something like this, shown me here. And now we can see the barrier here is become smaller. And once we have the smaller barrier, the barrier actually is become the VBI minus VA. So once we have a smaller barrier, which suggests the electrons here can start to flow to the left, and also the holes here can start flow to the right. And therefore, based on this band diagram, we can expect that our IV curve, which IA, VA here. Previously, we mentioned under reverse bias, there's no current. This is in the case where VR equal to minus VA. But now we have a forward bias, we can start to see the current flow. So the expected IV curve will be shown in here. And when the voltage is larger than certain turn-on voltage, this is a VT turn-on voltage here, then we will see the forward current, and this is a point VF equal to positive VA. And therefore, under the forward bias, we expect to see the current conducting in this PN diode. So therefore, the PN diode becomes a two-terminal device that can be conducting on the one side, and under the another bias, there should be no current here. So there will be diffusion hole from P region across the space charge region where they will flow into the N region. Similarly, there will be diffusion electron from N region across space charge region flow into the P region. Well, the text sometimes difficult to digest, but in the end, the phenomenon is pretty explained here. And in the end, the most important conclusion is that finally we see the current through the PN junction, and that's a typical IV characteristic for diode, that we will have the forward operation, we will have the reverse operation. So that would be the goal for this chapter, that from the physics base we can understand, because it's not that difficult, but we need to try to make sure that our physics based speculation is correct. So how do we make sure our physics-based speculation is correct? So the next one is we start to need to have the mathematical equation involved. So we need to use a mathematical equation, analytical calculation to prove that our physics-based speculation is correct. I need help, so someone just help me to open the AC. Okay, so the next is we start to open all of them. So we just need to start to estimate find a way to calculate the PN junction current, and we'll start now. Is just a lot of bunch of equation will start to coming up, but the conclusion is, I already said, it's going to just to prove that our speculation is correct. So we're starting from the idea current voltage relationship for PN junction is derived on the basis of the four assumptions. The first one, we consider this is an abrupt depletion layer. So we consider the abrupt depletion layer approximation applied. The space charge region have a abrupt boundary, and semiconductor is neutral outside the depletion region. And the second one, we consider the Maxwell-Boltzmann approximation. Applied to the carrier statistics is something that we have been mentioned, and also we consider this is only the case with a low injection. And also completely ionization. And the total current is a constant throughout the whole system. The individual electron hole current on continuous function through the PN structure. The individual electron hole current are constant through the depletion region. So here is some of the term that we very often we will use later. So we have NA, which is a acceptor concentration. We have the ND is a donor concentration, and we have a N0. This is a thermal equilibrium. This is the equilibrium. Thermal equilibrium majority carrier concentration, and PP0 is a thermal equilibrium majority carrier hole concentration. We also have NP0. This is a minority carrier. So this will be more easier understand. We just plot as a P N here. So the majority is PP0 N 0, and the minority is NP0 and PN0 here. So that's this term is defined, shown here, and the rest you can just look at by yourself. And because for right now, we also will need to take into account as a space dependency. So later we will also need to consider that the concentration at a certain location. That's why there is a kind of the function of the x here. So as usual, we're starting from the very basic that we have the built-in voltage equation shown here, and we consider this term, this one, which is this ND is N0 here, and therefore because we consider as a complete ionization here, so therefore the NP0 can be approximate as Ni square over Na here, and this one, this is, we consider this one, and normally we have this we consider this one, so this will be equal to NP0. So therefore the NP0 can be estimated as a N0 exponential minus VBI over KT. what does this equation tell us? This tells us that the minority carrier electron concentration on the p side to the majority carrier concentration on the other side. So this is actually, we can have this equation to estimate the minority carrier concentration and majority carrier concentration here. So this is also just try to be a little bit clearly for you. Is this equation provide us, we have the P and N. So this P0, that's a minority carrier concentration on the N side, can be also estimated from the majority carrier concentration. Minority carrier concentration on the P side can be estimated from the majority carrier concentration on the N side. So the rest of the discussion, the calculation is not that complicated. The only complicated is that we have a lot of NP0, NN0, PN0, PN0, and this term, to be honest, is a little bit confused because of, if you try to put every term, like the NP0 is the full definition is the minority carrier concentration on the P side, and then the NN0 is the majority carrier concentration on the N side. So you see that this is a little bit confused. So I think that's the most difficult part. But the rest of the calculation is very simple. You just need to a little bit calm down, take a time, try to think about this. Okay, so now we just try to do this day by day. So we have a NP here, which is shown me here, and then because this is under the forward bias condition, and therefore the forward bias tells us that where we have been shown that this is a EFP, and this is a EFN, EFP and EFN, and we all knew that the difference in here, which is mainly related to our forward bias here, and we have been shown the band diagram. So this one is EVBI minus EA, and we just put this back to here, where this is minus EVBI minus VA here. And with this equation, we can expand as this one and this one. And also this term can be further considered as NP0, where therefore our NP is equal to NP0 exponential EVA over KT. Which this is this one here. And similarly, finally, so our NP can be equal to the NP0 times exponential EVA over KT. So the same, the PN is equal to PN0 exponential EVA over KT. So the goal is that originally we already knew under the equilibrium the minority carrier on the N side and P side. So, but now we want to understand the voltage dependency. So original under the thermal equilibrium, so we already knew the minority carrier in the P region and also the minority carrier in the N region. But now because this is under the bias, which is the VA, forward bias, so once we apply the forward bias, we want to understand because once you under the forward bias, for sure that we can expect that the minority carrier concentration should be different, right? Because it must be certain carriers start to flow. So in the end, we want to understand the NP and PN here. So that's a goal. So as I say that the calculation is not that complicated, but just the denotation, the term here sometimes just a little bit confusing here. So it's just try to help everyone to understand our goals behind. So now we understand that this is thermal equilibrium, this is under the bias and under the bias, and then the only difference here, just exponential. I should not use this color because it get confused. Just exponential EVA over KT. That's all. So with additional exponential bias over KT, we are able to calculate the minority carrier under the forward bias case. So now we start to move to a little bit complicated because in this PN junction, we have to always aware that this is a consideration that we have the electron and holes that both exist, both generative, both diffusion. So it will be good to also understand the space diffusions related to these carriers here. So now again, we consider as a PN junction which we have a P, we have a N here, and in the middle we have the junction interface here, and also we have the space charge width, depletion width boundary, or something like this one. And so we are interested in as a X along the X direction. Along the X direction, the minority carrier diffusions, a minority carrier distribution along the X direction, where we can start to state by state to create this graph, which in the middle we have x equal to 0, on the right x equal to xa, on the let me check, xn, and on the left minus xp. And because right now we are trying to understand the minority carrier, right? So we have to start to think about what could be the minority carrier distribution inside this PN junction. And first of all, just consider as a thermal equilibrium case. So in the case with thermal equilibrium, in the P region, we have a thermal equilibrium minority carrier which is NP0. So therefore, first we can plot the NP0, which is shown in here. Similarly, we can first to draw the PN0 here. PN0 here. One thing you might be curious at why the NP0, PN0 is not flat, because in here we consider this is a junction which is a P plus N. Because a P plus N, you know that we have a very famous equation that under the thermal equilibrium, N times P is equal to Ni square, right? This is a case with thermal equilibrium. So which means that you have a higher P plus, for sure you get a lower minority carrier. You have a lower N, that's why you get a higher PN0. So in every textbook they draw in this way, that this never be the equal, it's always this a little bit lower than this one. And the reason behind is because of, in here we consider the P plus N here. And now we try to look at the under the additional bias. Just go back to remind everyone that our goal is try to have the case once under the forward bias, what would be our minority carrier here and here. So in the case of X equal to XP, we can have the minority carrier at this boundary condition minus SP still will follow NP0 exponential EVA over sorry, I should, because for the later illustration it's better that we should this one. NP at this boundary should have the NP0 exponential EVA over KT, which is this one. This is a minority carrier at X equal to XP under the forward bias. So similarly, we should be able to estimate the minority carrier at the Xn location, which is Pn0 exponential EVA over KT here. And why we have this? From the mathematics, we show this already, right? From last slide, we derived this equation. From last slide, we derived this equation. But physically, how do we understand? This is actually the electrons injected from the N side. We have the electron under the forward bias. The electron will start to diffuse, right? Because our barrier is reduced. So electron is able to cross this barrier and reach to this side. And once the electron reach to this, they become the minority carrier. And therefore, this is actually the electron injected from the N side will become as a minority carrier, but this minority carrier will exceed the background doping. So that's as considered as a excess minority carrier. which is here. This is excess minority. So now, finally, this means electrons injected from N side becomes excess minorities in P side. So let me explain again. Under the 4 bytes, our barrier is reduced. So finally, our electrons able to flow to here. Electron originally are the majority carrier on the Pn side, but once moved to the P side, they become the minority carrier. But also this additional electron is not originally in the P region, it's an additional one. So this electron becomes the excess carrier. So finally reach to this region, this electron becomes as an excess minority in the P region, as shown here. So that's what this graph want to illustrate here. So finally, we can all apply. If you can follow this one, then what we learn from the non-equilibrium excess carrier, all the concepts are the same. Because later, if you look at the later slide, you will find that all the equations are the same. It follows the same exponential decay. It follows the same which we consider excess carrier minority, because this one is just an application of the previous knowledge. And also, finally, this excess carrier, excess minority is equal to NP minus NP0, right? So if you can follow, actually this equation is again, and the illustration here is not that complicated, just you need a time to think about this, try to digest it. So similarly, we have the holes here. Because the barrier is reduced, the hole finally is able to move to the right. And once to reach to the N side, the holes become the minority. And this hole is additional hole, therefore this is excess minority, right? So therefore, the concentration here actually are the holes injected from P side become excess minority in N side. And this excess minority is delta Pn is equal to Pn minus Pn0. So now, with all this knowledge, actually we will start to do the same things that we already learned from the slides, from the excess carrier, because we are going to do the exactly same calculation. Okay, so again, we consider the minority carrier distribution based on this and bipolar transport equation for excess minority carrier holes in and N region. So we have this equation that where we already shown before. And the first one is space. We have the X, which is a space dependency, and also T, where is a time dependency, right? So we have the related to the space, related to the time here. And also we have this excess minority carrier hole, the excess minority hole carrier concentration here. And bipolar transport equation is describe the behavior of the excess carrier as a function of the time and spatial coordinate, which where we shown here. This is related to the T and X here. Now, as usual, we will try our best to simplify the question here. First one, we assume that electric field is 0 in the neutral N and P region, because this is there's no the electric field is 0 here, so the E is equal to 0, and also there's no electric field, so the additional generation G prime is also 0 here. And also we consider the steady state, which are time dependency of this delta Pn should be equal to 0. And with all these assumptions, so we can simplify the equation, become this one. Second order derivative of delta Pn minus this one, delta Pn ln Lp squared is equal to 0, where this one Lp squared is equal to dp tau p 0, and also second order derivative of the np dx squared minus delta np over ln squared is equal to 0. Where is this one? So this is already the equation where we have been shown. So finally, with all this equation, and also considering the several boundary conditions, so we have this one, the boundary condition. First, with these two equations, we can have the general solution with different space. This is a different location. We have this x larger than xn, and then the x smaller than xp. And we consider the 4 different boundary conditions. BC1, this is BC1, and BC2, boundary condition 2, and also the BC3 is here, and BC4, this is BC4. So with all these boundary conditions, we are able to start to calculate So finally, we can get this conclusion that the minority carrier concentration x equal to 0, xn minus xp, we have this np0, pn0, this is np0, Pn0. This minority carrier, and then on the boundary here, we have this Npx also. Pnx here. The minority carrier concentration decay exponentially with the distance away from the junction to the thermal equilibrium value, because the equation here, this is exponential. So therefore, the distribution of this minority excess carrier in the P side is here. On the N side is here. We have this exponential decay. And then for this excess delta Pnx, delta Npx, sorry. This should be the delta Npx. This should be the delta Pnx here. So in the end, the conclusion is very similar to what we have learned before. We have this exponential diffusion for this excess minority carrier. So again, because of we have these excess carriers here, we have an excess minority here, excess minority here. That means this is not an equilibrium case, so we cannot use Fermi energy. Excess in the neutral P and neutral N region here. This is excess, right? So because we have the additional generated, this is excess carrier and excess carrier here. So we must have to use the quasi-Fermi energy. Where that we already mentioned in the previous in this region we mainly use a quasi-Fermi energy. Now we get another proof that we will use a quasi-Fermi energy. So therefore, your P is equal to thermal equilibrium plus the excess carrier is equal to Ni exponential. EFI minus EFP over KT. And also the N is equal to N0 plus delta N is equal to Ni exponential EFN minus EFI over KT here. And then the EFP and EF, this is quasi-Fermi energy. Because the carrier concentration are exponential function of the distance, right? This is exponential function of the distance, and therefore in the band diagram, in the end will become the linear function of the distance in the neutral P and N region. So therefore, if you try to plot this, you will see this is EFP, EFN. and the P region, this is a P region. This is P, so close to valence band. This is for the EFP even, this is also the Fermi energies here. So that's a typical case. But now if you try to plot the Fermi energy, quasi-Fermi energy, first of all, quasi-Fermi energy will be the constant in this here. But because of we have the exponential decay, so therefore this will become as a linear function. This will become linear function. To be more precise, this should not be below the. This should not be below the. Okay, so that's why that you see the quasi-Fermi energy in the P and N region was shown as a linear. This linear is because the distribution has exponential decay. Okay, so we will stop here and then just some more reminders. So we will have an exam next week at 10 a.m. on this morning. Please come as early as possible because I expect this classroom will be very full if everyone come for the exam. That should be the full, so you should come earlier. So yeah, and then we will immediately start the exam. If everyone come here, everyone's ready, we can start earlier, then you will get some more time. But otherwise, we will start on time at 10 a.m. And also reminder that tomorrow and Thursday at 6 p.m. Tomorrow is in this classroom. On Thursday is in the classroom next to this one. We have a TS session, so you're welcome to join to ask any questions. They will also explain the homework. Okay, thank you.